good morning everyone. Thank you all for coming. So I am going to talk about, on this topic, technologies for science for life beyond Earth. Now, one of the questions that we always want to answer is, are we alone? Professor Supriya said just now that we are going to hear about the advancement of technologies that have been done primarily in the United States. However, the quest for exploration is not limited to any countries. It is a human quest. We all want to know. The basic question that we want to answer is, are we alone? How much do we know about that? Are we alone means that, are we alone? Does life exist only on our planet Earth? Does life exist beyond this small planet? If you ask me, I'm asked this question several times, that what do I think? Does it really exist anywhere else? My answer to that is, it should. Why? Why should it exist? Think about it. The reason is, our planet, and if it has sun, we have 8 planets in our own sun. One point of time we had 9. Pluto is not a planet anymore. And we belong to a galaxy called Milky Way galaxy. And you know how many stars, like our own sun, are there in that galaxy? 100 billion or more. 100 billion. 10 to the power 11 to about 10 to the power 12 number of stars are there in our own galaxy. There are 100 billion galaxies in our universe. So somewhere between 10 to the power 22 to 10 to the power 23 number of stars are out there. Then what is the probability that it might exist one star, right? There is a planet that has life. If you are a student of mathematics, all of you are, all engineers and scientists are all mathematicians in a way, then you start thinking about the probability. Probabilistically, it has to be there. There has to be another planet where all the environment, all the situation is such that it sustains some form of life. And that's what we are looking for. So let's begin that journey together and see what we have learned so far. Before I start, I want to acknowledge the group that I work in at NASA Jet-Propulsion Laboratory. Okay, where does NASA Jet-Propulsion Laboratory is located? NASA. Coming sounds. So, NASA is National Aeronautics and Space Administration. Started about 60 years ago. But where I work at Jet Propulsion Laboratory, JPL, it started more than 80 years ago. Actually, NASA started from JPL. JPL is one of the labs for NASA. It is in Pasadena, California, in Los Angeles. NASA has several laboratories all across the United States. And our headquarters is in Washington, D.C. But JPL, Jet Propulsion Laboratory, is the largest laboratory of NASA, where we have about 6,000 people. And we do all robotic missions. That means all the missions to Mars and beyond, where no human being, we don't send human beings from our lab. We send robots. We send instruments to outer space. That's where I work. I also work at California Institute of Technology, Caltech. I talk a little bit more about it. Caltech is a very small university. How many students are there in Cochin University? Does anyone know? 5,000. Caltech has total 2,000 students. 900 undergraduate students, they're doing BS, BTech, and 1,100 graduate students, they're doing their masters and PhDs. There are 600 postdoctoral fellows and 300 faculty at Caltech. Very small university by any standard. Caltech has produced 38 Nobel laureates. 38 Nobel laureates, 37% got Nobel Prize because 1% got 2 Nobel Prizes. Linus Pauling got Nobel Prize for chemistry as well as for peace. So a small university with 2,000 students has generated 38 Nobel Prizes. So it says something about it. You know, I was a graduate student there, and sometimes I used to pinch myself to see that is it a dream that I'm here? It is a wonderful place to work. And I'm so happy I was lucky that I got a chance. So this is the group that I work at KTL. We have about 24 people, and you can see that the faces, they're from all over the world. There is one Indian there, of course. You can see there. So, before we start, this is a picture of Mars. I said that there are 100 billion galaxies in our observable universe, and about 100 billion stars in a galaxy. These are rough numbers, order of magnitude numbers. Maybe there is more, but order of magnitude. In physics, you know order of magnitude is important. So Mars, why do we, if you hear from NASA, NASA is going to Mars, Mars missions happening, time and again, why? Why do we go to Mars? There is a specific reason why we go to Mars. One of the reasons is Mars is our closest neighbor. Right? Going to outer space is a very big challenge. So Mars is the closest planet we have. On the other side you have Venus. Venus is extremely hot. Surface temperature on Venus is 700 degrees centigrade. So what are the possibilities of finding life there? Not so much. But Venus is very interesting too. So we'll talk about that later on. So before we start, I want to show you a video. Hopefully it is going to work. If not, I'll have to try something else. This video is that we sent Mars rover Curiosity on planet Mars in 2014. I keep saying that, I also mentioned that before, that United States is the only country which landed something on another planet. No other country has successfully landed a rover or anything else on another planet. It is not that they didn't try, or it's not that they are not good enough. They are, but it's extremely challenging to land on Mars or any other planet. So I'll show a video. So when Curiosity landed, this video shows that where were you when Curiosity landed. It is some part animation, some part real videos. So it shows what it takes and the excitement that we have when something lands on another planet.
Things look good. Vehicle core center interface. At this time, begin pressurizing the propulsion system to increase the thrust of the system. We'll use that for roll maneuvering in the atmosphere. We're about to.
This was around midnight in Pasadena, California.
We're setting started guided entry. Navigating to feel the atmosphere as we go in here. The vehicle's just reported via tone that it has started guided entry. At this time, the vehicle is beginning to steer its way to the target. You can see peak deceleration. Starting its first tank burst. It is reporting that we are seeing G's on the order of 11 to 12 Hertz G's. Starting. We don't have any telemetry velocity. We should have correction deploy around Mach 27. Correction was deployed. let's count the ground command. We're down to 90 meters per second at an altitude of 6.5 kilometers per second. Standing by for batch separation. We are in powered flight. We're at altitude 1 kilometer per second. Standing by for sky training. Sky training started.
Single nod, can remain strong.
Touchdown confirmed. Proceed.
Got thumbnail.
So every time I see this video, I still choke up. One of the reasons is that when you work on something, and then that successfully goes to another planet and land, this is really, so that is so exciting. And you could see that even grown men cry. They behave like kids. They're all jumping around because you work on something for years and then it successfully lands. One of the challenges is that it takes 7 minutes for signal to travel from Mars to Earth. So we do not have, all real-time information what's going on, whether it has really successfully landed or it crashed. We have no idea. So we get information that comes in and then we move forward to the next one. So that's how it works. And what you saw there's so many challenges that we have to solve to be successful on that. In previous missions to Mars, we always flown very small. I'll show you some of the sizes of small instruments. The first rover that we landed was a very small one. And then it started becoming bigger and bigger. So in the first one, when it landed, what happens, you drop that. And then we had a kind of a balloon kind of structure where inside the rover was there and it bounced on the surface and then came to a halt. Then it opened up and the instrument came out, the rover came out. However, this one, Curiosity, was so large that no balloon would survive. So we had to come up with a new idea. And someone said that we should have a crane. Did you see at the end, actually something actually lowered that? He said, okay, we should have a space crane that should lower the thing on the ground. So you saw that there are some jets coming out but you cannot go all the way to the ground. The reason is when the jets are coming out, Mars has a lot of stones. So they will come back and destroy your instrument. So you cannot really go all the way down with that. So someone said, oh, let's use a crane. It will lower that and we cut the cord and it will fly away. That it will work very well. And everyone said, are you crazy? Crane on Mars? So we tried that first on ground. So what happened is near California, we dropped something and the crane and didn't work. It went all the way down straight, boom, all got destroyed. But still we started working on that and eventually it was successful. So that's what drives us. that the technology helps us answering some of these questions, but we'll have to be innovative. Supriya Madam was saying, or your Vice Chancellor was saying that we'll have to innovate. Innovation is the key, and we need, NASA needs all of you, all the students, doesn't matter what you are studying. We need biologists, we need electrical engineers, we need physicists, we need chemists. Every single discipline is needed to make this exploration. And I am there, I'm working there, so you can come too. So that's what we always ask students to come and work. So okay, why do you go to Mars? Because Mars is very similar to our own planet, at least in its early universe. Look at this, this is the real scale. So this is our planet Earth. So Mars is slightly smaller than our Earth. But the question that we keep asking, was Mars ever a habitable planet? So let us set the baseline clear. We have not found life anywhere else other than our own planet. That is the baseline. Whatever you read anywhere else, those are nonsense. The reality is we have not found any form of life anywhere else. No one has found it. So if you don't believe, if you read something else, because we have not found. But question that arises, that was Mars ever habitable? That's why you keep going back and want to learn about it. If I show this picture to people, look at this picture. This is actually not from our planet. This is from Mars. If you look at this, you will find that this kind of terrain we get only when there's flowing water, not otherwise. Which means at one point of time, on Mars, there's flowing water. But if you go to Mars today, we don't see that water. We see water under the ground called thermofrost, but not flowing water. So something happened there, and all the water went away. One of the questions is, what happened? And when there is water, was there life? Can that happen to our own planet? What can we do to prevent it? So those are the questions we are trying to answer, and that's why everyone, all of us together, we are exploring more and more. So before I go and talk about finding life on another planet, so I want to show two things that Curiosity did. That after it landed, this is a picture of our planet Earth. If we expand, you can see the Earth and the Moon. This was the first time we pictured our own Earth from another planet, surface of another planet. This is really exciting, right? So sometimes we work on small things in our lab, and then you should always keep the big picture in mind, because one day that small thing that you worked on went to an instrument, that instrument went to another planet and sent a picture like this. So that is really exciting, excitement for people who are working on those kind of systems. Another one is that Curiosity, what it did, it had a very high definition camera. It took a lot of pictures, and it captured for the first time eclipse of 2 moons of Mars. Our planet has only one moon, our moon, right? But Mars has multiple moons, and Curiosity, for the first time, it captured the eclipse of 2 moons on Mars. How exciting is that? But it did not have a very high definition camera, video camera. It had only a still camera. So what we did, we put together a series of pictures in a video format to show this. So this is the bigger moon, and this is the smaller moon, Deimos, and this is Phobos. You can see there is this eclipse of the 2 moons. So we put together, about in 55 seconds, all these different pictures. It was done in August 1, 2013. So again, that is very exciting for that. So again, we go back to Mars closest, and it appears that the Mars could have life at some point of time. We don't know yet, so we keep going back. So I was saying the first one, Pathfinder in 1996, was this size rover. Look at the size. Then Spirit and Opportunity, 2 rovers that landed on 2003 was like this. And then Curiosity, 2011 became. This is the size of a Hummer car. It's kind of a lorry. So we landed a lorry on, on Mars. And that's why it's extremely complex. You can see the number of instruments that is there. And this is one of the, talk about smart cars, self-driving cars. This is the most expensive self-driving car in the world. It costs only $2 billion. But it has a lot of other instruments, of course. It has a lot of cameras, there are a lot of, it search for biological molecules, geology and geochemistry. And idea of that, when this was proposed, well, what science is going to do. So we had this Curiosity's primary scientific goal is to explore and quantitatively assess local region on Mars surface as a potential habitat for life. Was there life in Mars at any point of time, or is there life today? So that's what Curiosity did. We are going to have the next Mars rover on Mars 2020. It is very much like Curiosity, but more advanced instrument that's going to be launched in 2020. You can see there are 23 total cameras on that instrument, and 9 of them are engineering cameras. Scientific cameras are 7, and 7 cameras are entry, descent, and landing. So we need all these. This has obstacle avoidance because Mars has a lot of big stones and boulders, so it needs to go around on its own. We cannot drive from here, as I said, because it takes 7 minutes for a signal to reach there. So if it encounters a stone on the way, we cannot tell, okay, make a left turn. It's all too late. Right? So it has to make decisions on its own. And that's why it is an extremely smart vehicle. It does that. Okay, now this is the history of our universe. We know that scientists believe we started with the Big Bang. This is the Big Bang theory, not the Big Bang theory you watch on TV. Some of you do, I know. Sheldon Cooper, he works at Caltech, and the Big Bang filmed oftentimes at Caltech campus. So I see them. So this is the history of our universe. It started with the Big Bang, then there is a rapid expansion, and then the first light of the universe came out about 400,000 years after the Big Bang. The first galaxies were formed about 1 billion years after the Big Bang. And this is our current age of the universe is about 13.85 billion years. We know that accurately. And then if you look at the visible universe, this is the size. This is the size of our visible universe, because we always say it's the ever expanding universe, because it grows. If there is an explosion, things move away, right, from the center. That's what is happening. It's growing, expanding, and there are new stars and new galaxies are formed every second in this universe. And as I said, there are 10 to the power 23 stars out there. Can we find life? Before I go there, if you think about it here, a lot of new things happen when with a lot of new theories, and we actually keep proving that those theories are correct. We believe that there is gravitational waves were created at the beginning of the universe. Gravitational waves are one of the fundamental waves, like electromagnetic wave. So, but we had never detected it before. In 1996, Einstein's general theory of relativity said that there has to be gravitational wave in this universe, but we had never detected before. But just after 100 years after Einstein's theory, 2016, gravitational waves are detected. And if you follow news, 2017 Nobel Prize for Physics went to 3 people for detecting the gravitational waves. And guess what? Two of them, Barry Barish and Kip Thorne, I know them very well because their office is very close to where I used to sit as a graduate student. They are from Caltech. They got the Nobel Prize along with Rayner. He's from MIT. These three people. So if you work hard and keep your eyes on the ball, you might get Nobel Prize. They worked for a long time actually. It started a long time ago. It's called LIGO instrument, laser interferometer for gravitational observatory. LIGO instrument. They spent a lot of time and eventually they got the Nobel Prize for their work for detecting the gravitational waves. So, and this is the signal, first signal when how these gravitational waves were created was when two massive black holes collided and they generated the gravitational wave, and that's what they detected. This is actually an audio level signal. You can hear it, this signal, because if you look at the frequencies that are in the audio domain, you can chart that you can hear of gravitational wave, very low frequency signal. But it is a very different kind of signal than a wave than anything else. Electromagnetic waves is impeded by obstructions, right? If there's a wall, it doesn't penetrate that well, electromagnetic waves. Gravitational wave goes through everything. You cannot stop it. So that is the beauty of that. So can we use that kind of wave for something else? For communication? Who knows? We don't know. We'll have to create gravitational waves to massive things. So that is the problem. Okay, let's look at what are the chances of finding life on finding other planets. First we have to find planets, then we can look for life, right? We have just started. We are at the very beginning of finding planets. 10 years back, we had not found any planets outside our solar system. Now we have found more than 3,000 planets. But there are many more. So if you look at it, our closest star is called Proxima Centauri. It is only 4 light years away, not too far. You know what one light year is? 9.5 trillion kilometers. 1 light year. So to go there, it will take, it is not going to happen anytime soon. Let's put it that way. So we'll have to learn about all these from far off place, from our own planet. And it turns out that our closest star also has a planet. So this planet is 1.3 times the size of our own Earth, and it orbits in very fast. It is much closer to the sun, so it orbits in 11.2 days. But the temperature on the surface is such that we don't think life can exist there. So we look for planets which are, we call it habitable zone. What is a habitable zone? Habitable zones are such that the temperature on the surface of the planet has to be such that liquid water can exist in liquid form on the surface. If it does, then we believe that life might exist. Why? Because the life that we know needs oxygen and water, and that's what we search for. Someone might say, that could be life of another form. It's highly possible. How do you search for them? If you don't know what to look for, how do you search for them? You always search for something that we know about. We know our form of life, organic life. It needs oxygen, it needs water. That's what we search for, water and oxygen, right? There could be life of other form. We might get surprised, but we cannot search for that. We might stumble upon that. Always there is a possibility. The other star is this is the Ross 128 is the 12th closest star of our sun. And again, it is 11 light years away. Do your calculation. This is 16% of the sun's mass. The star that has some planet, it is less bright than our own sun. And it has a rocky planet. Again, what we have been found of the 3,000 planets we have found so far, majority of them are like Jupiter, gaseous giants. But gaseous giant cannot sustain life. We'll have to stand on something, right? So we are looking for rocky planets. How do we find planets? So that is a good question, right? So what do we do? When I'm telling you that we found 3,000 planets around other stars, how do we find it? How do you know about that? How do you know what is the orbit, how far it is from the sun? All this information. This is not fake news. It is all real. You'll have to actually do it. How do you do that? Most of these planets have been found something called occultation method. What it is that we look at, suppose you are looking at a star and you isolate the star, because this star is surrounded by other stars and galaxies, so you'll have to isolate the star somehow. Once you isolate that star and you measure how much total light is coming from that star, if there is a planet that goes around that star, when it comes in front of you, amount of light will dim, right? So if you measure that amount dimming of that light, then you can tell, oh, there is a planet. And then you start doing measurements. How much time it takes for that star, that planet to pass in front of that star. Then you can find out how far it is from the star. All this stuff you can actually start calculating based on the measurement that you have done. And then you can start telling more. What is the size of that planet? And then you started thinking what could be the temperature, because you can do calculation. You know the total amount of light that is coming from the star. Then you can tell what is the temperature of that star. From there you know what is if there is surface, there is rock, what is the surface temperature of that. These are all extremely involved process, because you can imagine a star that is 11 light years away, amount of light that is coming to extremely tiny, and then when it dips, when the planet passes in front of it, even smaller, that variation. So you need to have extremely high sensitive instrument to make this measurement. We are doing these measurements from Earth. Majority of the measurements is done from space, because of our atmosphere, it changes, because the twinkling of light, why that is happen, because of our atmosphere, right? So we want to move away from that, and we want to look at that very clearly. That's why we need space instrument to look at those stars and see if there's any planet. This star, that ROS 128, is small and cool. As I said, it's smaller, and this planet receives only 50%, but the planet is much closer to that star than our own planet. So it gets 50% more light than we. Right? So chances of life might not be that high. So we are exploring all this. Another system, Kepler 90 system, actually discovered by our Kepler mission. Kepler mission was launched about 5 years ago, and it has majority of the planets found was with the Kepler mission, because that was the first dedicated mission to find exoplanets. These planets are called exoplanets. Our planet, we were very proud people, the human beings, and we used to take, show off, saying that our system, we have the largest number of planets in our system. We have 8 planets, because so far we had not found any stars outside our sun which has more than 8 planets, not anymore. The largest one was Kepler 90, it had 7 planets. But recently, very recently, with again Kepler mission, we found Kepler 90I, another planet in the same system. So now it has 8 planets, same like our own solar system. but Kepler 90 is 2,500 light years away. And it has 120% mass and radius of our own sun. So the sun of the Kepler 90 sun, the star, is slightly larger than our own sun. But it still has all these different planets. If you look at it, actually this is not like our own system anyway. If you look at, this is our Mercury, Venus, Earth. This is our inner solar system that we call. And Kepler 90I is actually here. If in terms of real distance, you can see much, much closer to the sun. And the farthest planet, it is here. So it is of the order of the same orbit as our own planet. So this is much closer system. So if you look at this star is about 2 billion years old. So we can know, if we look at a star, we can actually find out what is the age of that star. This star is about 2 billion years old. Our sun is 4.6 billion. We know all these details. The surface temperature of this star is 6,100 Kelvin. Our sun, we know that, 5,800 Kelvin. But this star is so far away, as I said, 2,500 light years away. So it is too dim to see from Earth. We cannot see this star from Earth. We'll have to go to outer space. So we need more powerful instrument. We are learning, as I said, that so far we have learned hardly anything, because we just are scratching on the surface. So much more to learn on this. Another system that can, that can have possibility of life. If you look at this Kepler 90I, why we are so excited about Kepler 90I? Because the distance from the sun and all these details are such, we think it's too far away. We don't know much about it, but we think it could be a rocky planet. Again, this is a speculation. We do not know much about it because it's so far away. And it could be a rocky planet. And the temperature could be in the habitable zone. It's called the Goldilocks zone. It's possibility. Then we'll have to study more. Another system that has potential of finding life is called TRAPPIST-1 system. TRAPPIST-1 system is 40 light years away. Maybe one day we can go there. No. If we go by airplane, when airplane goes at the highest speed about 1,000 kilometers per hour or something like that. If you think about that, and it will take 44 million years to reach there by airplane. The sun of TRAPPIST-1 is 10 times smaller and 2.5 times cooler than our own sun. However, all these planets are much, much closer to the sun than our own planet. And it turns out majority of these planetary bodies, these planets, are in the Goldilocks zone. The temperature on the surface are such that it can have liquid water on the surface. There's another exciting thing about it, that they are all called tidally locked. What does it mean? You know that our moon is tidally locked with our Earth, which means we see always the same face of the moon. We do not see the moon is rotating, our Earth is rotating, the galaxy is moving around, but we always see the same surface of the moon. We have never seen from here the other face. It's called tidally locked because the way it moves is always show the same face. And it turns out for TRAPPIST-1, all the planets are tidally locked. So we always see only the same surface, it sees the sun, which means that even if the one surface, the temperature is such that it can sustain liquid water, other face cannot, because it will be too cool.
That will be great. In the summertime, stay here, winter time, no, other way.
So, but they are very close. You know, it is only the 5. If you look at this, 1E is only 5% of the distance between
Earth and the sun.
And this one takes about 1.5 days to go around.
We take how many days? 365 days, right, to go around the sun.
It takes only 1.5 days, and the farthest one takes about 20 days. These are all rocky planets and possibility of water. So
These are very exciting. This is the first set of planets that we found that where there are a lot of planets that can sustain life. So we actually have to look very closely to that. We look at how they look
a little bit more. So when we
started looking for this TRAPPIST-1 system, we had found only 3 planets. We found B, planet B, C, and another planet D. But we further studies realized that when we actually sent another instrument and started looking into that, we realized that when we saw the D, actually it was a combination of many other planets, because they're all moving together, right? And then we thought that is only one planet is blocking that light. It is not that. D was combination of E, F and G, E, F and G, and there was another H. So we actually discovered all of them. That's how we found all these planetary bodies. If you look at in terms of real scale, so this is the TRAPPIST-1 system. You can see here the size. In our solar system, the closest one is Mercury, but it's so far away from the sun. If you expand it, then you see here TRAPPIST-1 system. So this is 25 times enlarged. So much tighter and much cooler. So we are finding, so far, we are finding the planets which are in the Goldilocks zone, that is habitable zone, are much closer to the sun, and their sun is not as bright as our sun. That's why it can have the temperature, surface temperature, sustain liquid water. So that's what we have found, but we cannot draw any conclusion based on this, because how many you have found? How many more to look? Hardly anything we have looked into so far, and all these are our own galaxy. All the things, 3,000 planets that we found, they're all in our own galaxy, because we do not have the capability to actually find a planet in a star that is in another galaxy. This is too far away. Our instruments are not that sensitive to look into that. So much more learn. So this is a huge area that we actually keep looking at. So having said that, those are the places we can never go, at least not in near future, that's for sure. But we can go to some of the planets and planetary bodies in our own solar system and learn. That's why we go to Mars. Can you go to some other places? Can there be life in other places on our own solar system? The answer is yes. I talked about that other day.
this is Enceladus,
Saturn's moon. And what you see here is water pouring out. If you actually zoom on that area,
what you are seeing here is water.
this was
Discovered
by an instrument that actually we designed in our lab, and the mission is called Herschel Space Observatory, and the instrument called HiFi, and we did some spectroscopy imaging to find that water is coming out.
scientists have been really wondering for a long time that when we found water vapor on the outer ring of Saturn, you know Saturn has been
Saturn doesn't have any source of water. Then we would scratch our head, from where is water coming from? And when we looked into that, we found that Enceladus is actually
raining water.
I live in California, and California is going through drought nowadays. If our moon was like Enceladus. It would have been great, right? The moon rises, rains water, that's it. All problems solved. Unfortunately, that is not the case. And then the question is, so that if the water is coming out, it must have a reservoir of water somewhere, right? And then also, if we believe, we started looking into that closely, that there could be some energy also inside, because water in liquid, it is so far away from sun, so it's all cold. If water is there in liquid form, there must be some source of energy inside that is actually warming it up. So if there is source of energy and water, can there be life? What is in this water? Is organic molecules coming out? Is insects flying out from there? We don't know. We have no idea. So NASA is actually planning to look into that carefully and think that maybe one day we'll have a mission to Enceladus and see what is coming out in this water. We can learn something from it. Another area, another planetary body that can sustain life is, you can see water plumes spark the race to Jupiter, Moon, Europa. Europa is a Jupiter's moon. And also we have actually studied, very detailed studies of Europa has been done, and we found that like our own Earth, there is a mantle. Mantle means, hot core, right? Europa has a hot core. However, it is a extremely cold planet. There is ice shell, this thick ice shell here, and we believe there's a liquid water ocean underneath, because we found plumes coming out of Europa. So there's a liquid water ocean underneath this thick ice shell. The thickness of this ice shell is about 100 kilometers to 15 kilometers, so pretty deep. Is there life in this water? We want to find that out. My interest is that, is there fish? It's different, I love fish. So that is one of the questions. What can we do? What kind of instrument you can build actually to go there? NASA is planning a mission to go there. It will be launched in 2022 or maybe 2024. It takes 7 years to go to Europa. So by the time we reach there in 2021, all these things takes time. So even if we know something about it, it will be 2031, 2032. So long time away. But we are actually working on instrumentation to find out what is there in this water. Is there organic molecules? Is there life? Any form of life? See, we cannot send a drill to drill a hole and find out what is there in the water, because we don't have the capability of drilling a hole which is 15 to 100 kilometers deep for this kind of mission. So in our own planetary system, there are 3 places so far we know that either life exists at some point of time, or we want to find out. To Mars, but we don't know Mars still. Lot of things still to be known, because we have got only 1 or 2 places. If someone had landed in Sahara Desert, suppose some aliens, they come and try to find out if there is life on planet Earth, and they landed on Sahara, they will think, no way, right? Or Antarctica. Let's say, oh, this is also cold, there cannot be life. So that similar kind of situation is with us when you go to Mars. We have only 1 or 2 places. We are looking around, trying to find out if anyone is moving around, but we don't see anything. There is no Martian. That's for sure. So we are going to go there because we can, but it costs a lot of money. Because for a mission to Europa is going to cost in the order of $2 billion. It's a lot of money. In the newspaper recently they said, ISRO is much cheaper. I read it, Times of India day before yesterday. If Yesterday there was an article saying the ISRO is cheaper. I think that ISRO should do it. Should all or other space agencies to also invest in that, because only one team cannot do enough. NASA is limited. So all of us should have to put our hands together and make joint effort. Because if we share resources, we can do much better, right? Now the next question comes, okay, I talked about all this possibility of life, what we are doing. What kind of technology? Because here all of us, majority of you are engineering students and science students. So to do those kind of stuff, we need technology. So what kind of technology we need? We need to make everything small, low power, so that we can make many more instruments and go there, because it costs, launching mass is the main thing. 1 kilogram of anything to launch in space costs millions of dollars. So what can we do? Let's look at some of these. I'll spend next few minutes talking about some of the technology that we are working on to make it happen. We are actually very good at making things small. Historical, look at this. This is the first transistor, first IC, integrated circuit, that was done in 1960. It had 3 to 4 transistors. 3 to 4 transistors on first IC that was made. Then go to 1969. Intel made SRAM 56 byte. On your smartphone, how much is memory? If you have someone has 64 gigabytes, I'm not able to store all the videos. 64 gigabytes of RAM on your iPhone or Galaxy. This 256 bytes of memory in 1969 at 2000 transistors. And if you look at today, this is NVIDIA GK110 graphics chip IC. It has 7.1 billion transistors. So we are able to make this really hard and smaller, more and more. We are producing 10 to the power 19. This is to the power 19. We are producing 10 to the power 19 transistors per year. And that is about 1,000 transistors per every ant on the planet. And most of them work. But again, those are only cheap. We need other things. You all know, if you are an engineer, electrical engineer, you know that a chip is not going to do everything. We need other stuff. We need circuits. Everything has to be integrated. Look at this. This is 1917 Federal 1 megawatt pulse and earth radio transmitter with this size. You know what this is? This is iPhone 5, entire iPhone 5 circuit. Have you ever opened your iPhone or smartphone? Anyone? No? You should open it. Really, I did. I opened my wife's phone. Okay. Before you get too excited, it was so that's why I opened my wife's phone. But to open a smartphone is not easy, because you need special tools. So in US you can buy those special tools for $11. So I bought that and opened it, and it's amazing. Because look at this circuit. This has so many ICs, but the packaging, the connectors, how they put everything together is piece of art. That's why I said that if you are an electrical engineer and you have not opened your phone, you are not doing your job. Go back home, buy those tools, open it. It is very difficult to damage it. So be brave. Open it and see what is there. So you'll be amazed to see how beautifully they are all connected. So that is, we'll have to, that's what we do. And NASA also, we are doing it, because we have, of course, much more complicated thing that has to survive in outer space. Because if you send a phone to outer space, it's not going to survive, because of this radiation environment and all those stuff. Nowadays, if a little bit of water drops on your phone, it's gone. Not Galaxy 9, they are waterproof, they say. But open it up and put a drop of water on these and see what happens to your phone. But in outer space,
there's water, there's everything.
so your instrument has to survive.
So challenges are different.
But still, we are learning from them as well, that how can we make integration so that it's low power, low mass, so that we can make those kind of measurements more powerful, more sensitive. So this is important. So someone, as Professor Mohanan told me, that you should talk a little bit more about students, what can they do? NASA is more and more looking at CubeSats. You know, all our missions are big, huge, but CubeSats are shoebox size satellites. This is 3U stands for 30 centimeter by 10 centimeter by 10 centimeter. So 1U stands for 10 centimeter by 10 centimeter by 10 centimeter. So you can have a satellite which is so small and if you have integration like this kind of integration and good system, you can put it in there and make measurements. Then you can launch many more of them. That's what actually NASA is doing. ISRO is also very much interested in that. So you all should look into that. Can you build your own instrument? Because we need, say it again? Yes, it does. That's right. It did, but who launched it? Exactly. So you can, if college from Pune can do, why not CUSAT? Right? You should think about it. You should start working on that. You should not go around and tell people Pune did it. No, you should tell Cochin
can do that too. Let's do it. And ISRO will launch. NASA will launch. NASA has a program to launch CubeSat. You should do that. And you say again, these small satellites, we are trying to look at more and more. Initially, it was more for fun. The majority of the CubeSats are developed in the United States by undergraduate students who are doing the BTech. So that majority of them. But now we are actually looking at, can we put in more complex instrumentation in that small environment. So we are doing that. So I am working on some of these CubeSats as well myself. So there is a conceptual thing showing that what we are trying to do to measure the pollution on our own
atmosphere.
You all know that when you burn something here, in no time that pollution goes to the United States through upper troposphere. So we are actually trying to learn. That is the
Mission that NASA has that actually
measures all the stuff that costs a lot of money. So we are trying to build some instruments to measure that. So how the pollutants they transport through the upper troposphere. So if you one can say
that, oh, no, in our area we don't have many vehicles.
so it is not, if you want something, it is not going to pollute, but you are polluting everywhere else. So we don't live in isolation. So whatever we do, it matters to everyone else. It's true for everyone. That we are trying to build some of these instruments there. So also we are doing is a lot of a high level of integration. As I said, we are using silicon to make waveguide structures and integrating them in a very small package. Because planet, if you are to explore planet, it has to be really low power.
Mentioned the other day, per mission we have total 300 watts DC power available. Because if you have solar panels, if you are going to Jupiter, is far away from the sun, to get more power in a larger solar panels. And so larger solar panel means more mass. So we cannot do that. So we have total 300 watts. That we have about 10 instruments on average 20 to 30 watts. 300 watts means 3 light bulbs. Not much. So that's why we will have to make it low power. All the instruments has to be low power instrument. That's what we are trying to do in doing silicon micromachining kind of stuff. And we are also making CubeSat-based instrument. We just started doing, there's a video that actually showed the other day, is for students here who have not seen that before, that we have started making radar instrument on a CubeSat. It's a 16 CubeSat. and I started doing measurements. The idea is that it will have, we also need big antennas for those kind of CubeSat, but these are deployable antenna. Small antenna, this inside this, and it deploys so that it can get the data and send it back. So we are doing that kind of work. And I showed yesterday, I think, to you all that how we build that antenna and how it deploys. It works very well. So we deploy that like this. I'm showing this video because it's cool. When you see that, you like it. See how it opens up. That's how we make antennas. That is stored in a small space, but this is actually 50 centimeter antenna. It's large. We store only in 10 centimeter space. Then it opens up. And it works. This is actually measured data of that. You can make something looks cool and beautiful, but it has to work at the end of the day, right? So we can do that. And also we are making all other kinds of stuff. We need innovation. As Supriya Madam had said, we need innovation. Innovation is the key. And that's why we need young minds, young students. Because they're not afraid. You all are not afraid. We are afraid. As we grow old, we want to do something that will work. Because we are afraid because of our experience. But you all not. So that's why we need all of you to start thinking about what can you do, what is the next level you can do. Because there's so many more things to do, so many more things to learn. We don't know almost anything, right? If you think about it, in this universe, though I know all the young people also think they know everything. I know you think that way, but that is not the case. We hardly know anything. So many more things to learn. That's why we need everyone work together, join hands and work together. If you have any ideas, write to ISRO, write to NASA, write to everyone else, write to your VC that I have an idea, I need some money to pursue it, and see how it goes. With that, I will end. This some other structure that we have. With that, I will end. Very exciting time to make these discoveries. As I said, in the last 10 years, we found 3,000 planets, exoplanets, that we had not before. 10 years ago, people have started saying, we are not finding any planets anywhere. So maybe there is no other planet, only our solar system is unique. No. How can that be? Right? If you think about it, it's a random process. Then how can it be just one star, one planet has life? No way. So it must be that is our limitations that we are not able to find. And we know now it is our limitations. We have started looking, we have to look further and further and see how many stars are there. We have Kepler that has actually found 2,500 exoplanets so far. One mission and looked into such a narrow angle of our own galaxy. We need more money, more innovative ideas to do this, and we need all of you to work on that. Thank you very much.
Thank you, sir, for that very wonderful talk.
Can you make a small interactive section?
Yeah, I'm here. Yeah. I'm here for you. Ask questions. Sure. What is the idea? Right? If I talk, you listen, there is no point. Yes.
You said that
You are again, okay.
you said that the planetary system we found, they were very far away from us. And it is very difficult to find out the star itself. Then how do you find planets? That's even challenging. So
That's what I'm saying, that so far the technology that we have, the sensitivity that we have from Kepler, we found a star that is 2,500 light years away. We cannot even see that star from Earth, but you can see from outer space. Like, you know, if your eyes, what is the aperture? You work on antennas, right? So aperture size matters. What is the aperture size of your eyes? Hardly anything, small, tiny. That is your pupil. That is aperture size. And Hubble, what is the aperture size of Hubble? So it can collect much more light, right? So that's how we can actually see much further. But again, we are limited, very limited. And your detector has to be sensitive enough that when the light dips little bit, we'll be able to know how much it has dipped. From there, if the planet is really tiny and going around, we won't be able to see the dip. So that could be, that's why when we see these kind of things, we say, okay, there are 5 or 7 planets. But then maybe there are more planets, maybe there is a small planet, and the light dips little bit, we cannot detect it. So that's how we do. This is called coronagraphy. Coronagraphy, what it does is actually isolates the star. We'll have to isolate the star first, because there is so much of light pollution, because billions of stars are going at the same time. How do you isolate that single individual star? Yes?
Would you comment on Elon Musk's work?
Oh yes, Elon Musk is trying to launch things, and NASA is helping.
Already launched, it seems.
Yeah.
Already launched.
Yes, recently they also launched. So there's a great opportunity, because one of the mandate for NASA is that we do science and research, and when you develop technology, we give it to industry. So NASA is giving a lot of money to Elon Musk company, SpaceX, and a lot of NASA people are working in that as well. So they're looking at the commercial aspect of it, that everyone wants to go to outer space. And NASA is not in the actually business of sending people to outer space for commercial purposes. We are trying to do science. So that's why these private ventures, not only Elon Musk, there are many other companies, Virgin Atlantic and others are looking into that as well.
So I have one question, sir.
Yes.
Like it's like the idea was life is existing in this continuously inhabitable distance from the sun. That's where the Earth stays. So here, this Enceladus,
yes,
which is, you said, the planet, the satellite of Saturn.
Yes.
You said it's raining down water.
Yeah.
Right. So where the idea is like, you said it is like, something which is generating heat and the water is coming, because it should have been frozen since it is
that's
water,
right, that's right.
So it's raining down as water. So now, that means, the exploration now needs to be, it's just going beyond,
Yes.
all imagination.
So let me paraphrase his question. Very good question. What he's saying, that I mentioned that when you are looking for a planet and we are trying to say if it is habitable zone, we are saying that we have to see if the surface temperature has to be such that liquid water can exist in liquid form on the surface, right? Enceladus, there is no liquid water on the surface. The temperature is such that liquid water cannot exist. But still, there is a possibility, because we are looking at inside, we found that water there, something is coming out. So there could be planets which are not in the Goldilocks zone, but there are so many of that. What do we look for? We'll have to start somewhere, right? And they're so far away. Like Enceladus, you can go, and we got lucky that we saw something coming out, right? And we cannot see that from here if there is some water coming out from another cold planet, far off. How do you know if the water is coming out from a cold planet or not? From here we cannot find out. We'll have to go close, right? We are hardly able to detect if the planet exists by when the light dims little bit. If the water is coming out, we won't know. So yes, after we have more technological advances, we are looking for atmosphere. You know what we have to do for TRAPPIST that I showed? We are looking for atmosphere, because another important thing is, first of all, you see, is a rocky planet. If the temperature is in the Goldilocks zone, next, does it have an atmosphere? And what is there in that atmosphere? What is the content? Our atmosphere is such that actually it allows us to have life. We have nitrogen because it prevents cosmic rays to come and destroy life. If we didn't have any atmosphere, we won't be alive. We won't be here.
There's just one thing. I just want to. You said the oxygen and water.
Yeah.
I mean, like water is definitely essential. I mean, but oxygen, there are anaerobic forms in microbes.
That's right. That's right. There is anaerobic kind of life, but the organic materials, carbon-based life. I'm saying, but they are also carbon-based. So what we are looking for is the carbon-based life, and oxygen, because we think the high form of life needs oxygen. So at least that is our understanding, biological understanding. Yes, I'll come to that. Yeah. Yes, Voyager mission is the one that has gone outside our solar system and still continuing. Is going back. That is the furthest has anything gone. Man-made thing has gone out. It's a really exciting thing. The PI on Voyager mission was Professor Stone, Ed Stone, and he is a professor of physics at Caltech, and he comes and talks to us sometimes, and we are still getting data back from Voyager, but it's very slow. I mentioned yesterday it's about 1 bit per month or something like that, because it's gone so far away, and the amount of power that is available is so low that is very small amount of data we are getting, but we still know that it exists. Think about it, if it takes 7 minutes for signal to arrive from Mars to Earth, how much time it takes for data to come from Voyager to us? It has gone outside our solar system, but still works. Look at that, still working, it has not failed.
What is the power source? It's a nuclear battery, right?
Yes, that's a nuclear battery, but again, okay, let me then try to explain how it works. So communication, when your data is sent back, it depends on two things: the transmitted power. When you are receiving your power, also you have to have an antenna, large antenna, so that you can collect it, and depends on square of the distance. So as it goes further and further away, the power level that is reaching to you is almost negligible because it's so far away. That's the reason that it has power. It's not, if it was solar panel, it wouldn't work because there's no light. So it will be dead by now. It is working because it has a nuclear battery called RTG. But again, it's not enough power to send the data and a video of when it's going around. You cannot have a YouTube video from Voyager, unfortunately.
So can you just give how big are the probes?
Which probes?
The Voyagers.
Voyager probes. You can go and Google it, because many other people have many other questions. I think it will be better to do that. Google has everything.
Thank you.
Yes, go ahead. Yes. Yeah, astronauts, they are, if you talk to the astronauts, when you meet them, you are awed, because these are really highly skilled individuals. Majority of them, they are pilots. If you look around and find out the background of who are the astronauts, majority had been fighter plane pilots. So they are highly trained in flying something, because when you are a fighter plane pilot, you are used to this zero gravity kind of situation, because they have to dive suddenly and all, and they're so skilled, they talk so well, they know so much. So if you look at them, I always feel wow. So a lot of them I met, they come.
What did they say about being there?
So yeah, that's what that said that is the greatest experience of their life, when you go look at our planet from the space. And then also all of them say one thing that is so important. They say that when I look at that, our Earth looks blue from space, because of the Raman effect and all those stuff. We know that. He said that when you look at that, and then you feel our Earth is so vulnerable, we'll have to protect it somehow, because this is the only place we know in the universe so far that has life. So majority of them say that, because whenever they go up, they feel that more. Like people like us, when you go away from India, we feel so much more about India.
How does NASA look at the incoming visitors?
Oh yes, NASA has open arm. I am there.
Because we have been seeing so many pictures saying that aliens have landed on Indian vehicles.
Where are you reading them? Who is writing those? That's why I said first thing at the beginning, let's set the baseline clear. We have not seen any alien. Only alien we know that when you said, okay, non-resident alien came to United States. Oh, we are the aliens there. Yeah.
So what I've read, maybe you can cut for this. So stars that we see in the sky, we are seeing them because light has come from them light years and light years, right? So stars we see in the sky may be dead right now.
That's right, it's possible.
Right? So we are seeing the past.
Yes.
So we are seeing exoplanets and the Kepler system. So even if we find life, we might be seeing the past of life.
That's true, yes.
So we can't confirm life exists now. It could be like Mars.
What is now? When we see that, then we see this is now for us.
Yeah.
Right? We can, whatever you are seeing, maybe it is existed sometime back, maybe those life is dead and new life has come. But we can see what for us present is when we see it. That is our present.
There is no means to know right now.
Right now, how do you know? You have to go there.
Only way to do it if you go there.
Everything.
So what's the effect of gravitational
What?
matter?
What matter? Effect of gravitational wave matter? Gravitational wave is generated from matter.
From mass. We don't know yet. We have not, so far we found that there is no effect. Yes, right.
Hold on.
About Saturn and its moon, you said that
Enceladus.
yeah, Enceladus, the water coming down from the surface over. And in case of Earth, there's nothing, and the moon, there's nothing which comes down. Instead, moon's gravitation, moon and Earth's gravitation attraction causes tides in the ocean.
That's right.
So have we been able to understand what is the difference in the gravitation forces in both the cases?
Yeah, that the water that coming out from Enceladus, it happens on our planet. You know the geysers there. If you go to Yellowstone in the United States and India also, many other places, it shoots out, water shoots out, right? And that one is bigger. So we have that. Why does it happen? Because there is a source of energy and there is a venting system that is there. It creates enough pressure, then it throws things out against gravity. Gravity is trying to pull it back, but still the force is so much that you have to go against gravity. So that's what it happened. So in moon we haven't found anything. Moon is a kind of a very benign place. There's not much, at least so far we have learned, not much is happening on moon. Yeah, go ahead.
A few days back, I watched a video. It was about Elon Musk only.
Yeah.
So I watched in a video that there's all these missions to Mars, outer space missions. He has a plan of building a society, a colony in Mars, and there must be other people also who might be trying to do this. So in a general view, is this possible after some time Earth becomes inhabitable? That's not a near future, but is it possible that the exodus of mankind from Earth to some other planet or so?
Oh, there's a good question. He's saying that, okay, when Earth becomes inhabitable, he wants to go to Mars. So right now Earth is habitable. Mars is not. Yeah, if we find something that is habitable, then we'll think about it. Sure, then how to go there. But think about it. Right now, if whatever you say, the best place to live is planet Earth. Right? Yeah.
My view is more about theoretical rather than much more
Okay.
It's like we are looking for infinite number of possibilities.
That's right. Yes.
For limited resource
Yes.
management.
Yeah.
But we are looking for infinite things. That's
Yeah.
not true. But I just want to say, can we limit ourselves to a particular thing? It's like this, even the disorder has the pattern.
Yes.
So I believe if there is life, there must be some pattern.
Yes.
There must be some significance.
That we are.
So why don't we look for patterns?
Yes, people are looking. The question that he was asking that you couldn't hear was, he was saying that there's so much of possibilities theoretically. Can we look at patterns and then search for it? No. To answer your question, that I said the Kepler 90I, that planet that was discovered on December 14th, 2017. Only a couple of months ago we found that planet. And you know who found that planet? An engineer at Google. Because NASA has all this data from this Kepler mission. And when you have a mission, amount of data we get is huge. And it takes an enormous amount of time to go through that data and trying to find out what is going on and all. And we actually gave that data to everyone. We said, we have this. If you are interested, look into that. There's a Google engineer, he's about machine learning.
Yeah.
So he actually trained his machine to look for planets. You have to look at the data and there is small dip. Normal eye, if you have to do, you have to go through all this data, it takes huge amount of time and resources.
Like processing the billion information.
All this stuff.
Yeah.
So that person, his name is Scully, S-U-L-L-E-Y. So he was very much interested in this. So he actually contacted NASA, said, okay, I want to look into that. Then some person helped him a little bit, and he done the machine learning, actually existing data where you have already found some planets. First he looked into that and run through his machine to see what is the strike rate, in the sense, can he really say, oh, my machine is detecting planets for existing planet which are already found, and found that he was having 99% success rate for existing planets. Then he started looking at other areas which has not been explored, and then he actually found there is a planet 90I, and then NASA went back and looked it more carefully and found, yes, he's right. So how do you do that? Pattern to machine learning. So these are the machine learning and all this. If you are a computer science student, as I said from the beginning, we need everyone. So computer science will play, machine learning will play a huge role in not only building detectors. After you build detectors, get the data, someone has to process it. We need everyone. So, okay, I'll ask you first and then I'll come back behind you. Yeah, not most, pretty close. Yeah, because the sun itself is not as hot as our own sun, is much cooler. So as a result, what happens, even if the planet is closer, like our sun, temperature we know, right? And if we know the Mercury is very closest to the sun, and it's so hot. But if our sun was much cooler, then Mercury would have been much cooler too. So that's the reason. So these suns are smaller and cooler. That's why even if the planets are closer to the sun, but still the temperature is not that high. That's the reason. So you are asking question.
Is there any experiment or research going on
Wormholes. What do you want to do with wormholes?
Because that is the only way we can travel to 112 light years or 250 light years.
Through wormholes?
Yes, sir, because this physical technologies can do that.
Yeah, I know where you are coming from. I hear this kind of question. Then someone asks me, what is your opinion about quantum this thing, blah, 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 blah. Right? Not a thing. I'm not actually trying to put you down. It's a good question. Yeah, wormholes exist. We know that. if we want to go from Earth to there, first we'll have to find a wormhole here, right, to transport ourselves. Where is the nearest wormhole? That is the point. It is not here. So we have to first go to the wormhole where it exists, and then it's, there is a possibility. So yes, a lot of work is going on wormholes and all. I know you watch the movie, right? Yes. Okay.
Hello, sir. Yesterday I told you about the Europa mission we were roughly designing.
Yeah.
So we had a kind of an ice probe which goes deep into the Europa ice.
How deep?
So we estimated 30 kilometers, and it would be
kilometers.
It would be a nuclear powered, basically a ice melting kind of drill that would go inside. And we were thinking of using RTG as the power source.
Okay, how much power you will need?
So we calculated that. What is it?
Okay.
800.
Let me stop you there. If there is life, we are trying to find if there is life, and you want to, a nuclear powered thing to go through basically nuclear explosion there.
We found that it only emits alpha rays because it's radioactive decay, not fission or fusion. So
I will never fly it.
But NASA itself has suggested such a probe.
Yes. RTGs are there. You know why? The reason is, one of the main problem, if you actually think about it seriously about this, is we'll have to be so careful about planetary protection that first of all we should not carry life from here, right? If we are going to another planet, another planetary body, how do you protect that we are not actually carrying bacteria or life from here and start life there? That is first thing. So NASA takes it so seriously that when we actually work on missions, if it's a lander, you won't believe what we go through, because there is a planetary protection team that they will cover everything and then swab and clean so that no bacteria or no form of life can go there. And the second thing is,
breathouts and all, everything in this enclosure.
that is we are not sending human beings to Europa, right? We have gone only to moon. Okay, even if we send it to human beings, we have to make sure that. And now the second thing we have to do is, we should not destroy if there is life there, right? So this is not, your idea is not very unique.
Yeah, I know.
Well, what to do?
Actually,
of course, you melt.
Has some kind of a model which works on a nuclear powered ice melting.
Okay. So why don't you write a paper on that?
So no.
Because it has to go through, why I am saying it has to go through peer review, so that others who understand this process will look into that, whether your idea is sane. So always there is something called sanity check. The first thing we do, it's actually very important. All of you, whenever you have an idea, first thing is called sanity check. I'm not saying you're insane. That sanity check means scientifically talk to peers who understand this better, and so that they will see what is the flaw there. Is there any flaw? Is there any other aspect of it? It's again not that people have not thought about having a nuclear powered probe that will heat through these, but when you start looking at the details.
So do you think an RTG would be powerful enough to do it?
No.
How
much? As I said, 300 watts. RTG also.
800 watts estimation.
800. Okay.
Kilowatts?
No. 800 watts. 800 watts. That sounds more reasonable.
But we forgot it's in here.
800 watts. Most, because if I know RTGs.
No, I wasn't saying about RTG's power. I was saying about the power required to melt all this ice.
800 watts?
No, I think it was kilowatts. Do you remember?
No. Let me give you an example. You have water immersion heater, a rod. Yes.
You can discuss the separately.
Separately, yeah. No. I'll answer to that question. Okay, so one thing is that immersion heater rod is one more question. 1 to 2 kilowatt. 800 watts. How much? Okay, you have a question.
Sir, you said about the occlusion based method you are trying to detect the planets. then the problem is that we can only see the axis-aligned planets. Or
I cannot hear you. You can tell me. I'll repeat the question. Without my microphone is not working very well. That's right. Yes. That's right. Yes. That's right. Yes. That is not true. Let me tell them. His question actually trying to measure, try to see if the planet exists by measuring the dipping of light when the planet moves in front of the star, right? He's saying that in that way we can only see the planet which are in the axis of our line of sight. How is that if the planet is going around in the other way or any other orbit, right? How many planets you have seen that actually goes in the other way? In an other way. How many you have seen? Not any. You know why? Because how the planets are formed in a disk. If you look at our universe, yeah, but if you are looking at the sun in any disk, then if there is any planet going in front of that, we'll catch it. Now, you said that if maybe we are missing something. Yeah, perhaps. What can you do? Do you have any ideas? It's not anomaly because this is, if the planet goes in front of the star, we can see the dip in the light, and we say that if something is going in front of it. What else it could be other than planet? Maybe asteroid, big enough asteroid? Possible. But the bigger asteroid, they do not have orbits. They keep going. So we see that it keeps coming back. Then we know. That's why there is a lot of process we go through to make sure. That's right. Yes. Yes, absolutely. So you have your question. Answer that.
Sir, are you guys just focusing on the planetary missions and extraterrestrial life, or is there any missions going on like Rosetta mission?
Oh, Rosetta, yes. Yes. So her question was that are we focusing on these extraterrestrial life, exoplanets, or we are also focusing on some comets like Rosetta mission. Actually on Rosetta, we had an instrument from JPL. It's called MIRO, Microwave Instrument for Rosetta Orbiter. What it does, Rosetta mission is actually done by European Space Agency, but from NASA contribution. So NASA had instruments on that. It went to a comet, 67P is the name of the comet, and the comet, comet we thought brought water to Earth, and then we wanted to measure the water on the comet, and we wanted to measure the ratio of different kinds of water on Rosetta. So we are doing, NASA has a huge portfolio of things that we do. We have a limited budget, but we have to do exoplanets, we have to go to comets. That's why I am saying, please go and talk to ISRO and your government, our government. So talk to them and tell them that they should invest more money, and we should join hands so that we can work together. Okay?
Thank you all.